All right, let's go one more step now, and let's review the connection between force and potential energy. Okay, we used to say this, that the force was mg and u was mgh, right, the potential energy. And this is a little different than what it should be, because really the force of gravity was negative mg, right? We left out the negative because we always knew that the force of gravity was down. And this should make sense, because if we have an object here and we lift it up to a certain height, we gave it potential energy. How did it get potential energy? Well, we must have done work on it. Why did we do work on it? Well, because we had a displacement up, but the force was down, right? The force was this way, and the displacement was up, right? You have to do work against a force if you actually expect it to have a potential energy afterwards. Okay, if you allow it to go this way, well, then it's going to gain kinetic energy, right? So you do work against this force, and so really what we could say is that the potential energy is the negative accumulation of that force, because again, you're working against that force. So it turns out when you look at the new way, again, we almost always drop the negative sign from the force because we know it's an attractive force. We just are a little sloppy with that. But if you accumulate that force, the potential energy should be the negative accumulation of that force over a distance. And again, we're integrating with respect to some r, and this is some dr. I know you're used to it being dx, but our variable isn't an x anymore, it's an r. And if you integrate this, those negative signs cancel, but when you do the power rule, you increase the power by 1 and divide by the new power. You get this, but you get a negative sign. And so our potential energy is negative gmm over r. And this ends up doing lots of things. So what happens? Well, you can describe this as a potential energy well. So you're down here. This is some potential energy function. Again, this is kind of a picture view of what's happening here. And here is the Earth's surface. Right, all that is inside the Earth. Right, this is the Earth. And we are located on the surface. And at this point, we have some negative potential energy. Right, if you just plug in mass of the Earth, your mass, and the radius of the Earth, because that's where we currently are, you'd get some negative. And what you have to do is that to escape the Earth's gravitational field, you have to increase, right? You still have to increase your potential energy, just like before. Going from here and going away from the Earth's surface was an increase, right? Was a positive increase of potential energy. Still here, except eventually, if you get far enough away, you get to a potential energy of 0, right? So if you consider the old way, you started at a 0 potential, and as you increase your height, you went to some positive. The new way, in this potential energy well, you start out with some negative potential energy, and as you go away from the Earth's surface, you still increase it, but you just end up going closer and closer to being 0, right? Look at the limit of u as r goes to infinity. In the new version, it's 0. In the old version, if you look at the limit as you get infinitely far away, you'd end up with an infinite amount of potential energy. Well, that causes a problem. We certainly can get really, really far away, but we are not going to have an infinite amount of potential energy. This new way of looking at things makes it so that the force of gravity decays over time rather than being constant, and allows this new idea. Again, this potential energy well is something that people would use a lot to describe what's all going on here. But again, it's not really that big of a shift. Instead of going from 0 to a positive, you go from negative, getting closer and closer to 0. If you look at the graph of u, right, this is our function for u. The graph of u looks like this. Here's our potential energy as a function of r. There's the radius of the Earth, and we're here. We're at some negative. And then as we get further and further away, we asymptotically just approach 0. If you look at the force here, again, look at the force. The force is going to be the negative rate of change of du dr in this case. This is a big relationship, as is this, is what we just decided, right? This is our new potential energy function. We already discussed that this was our new force function, meaning the force of gravity is this. This is potential energy. Lots of times when we use it in practice, we drop this negative sign because we know it's an attractive force. But think about it here. The rate at which you change your potential energy is opposite the force. And again, look at here. The force is down. If you try to increase your potential energy this way, the force is going to be down because you have to work against a force if you want to actually store potential energy. That's the same thing on springs. Look at springs. Force is negative kx. Potential energy is positive 1/2 kx squared. Take the negative derivative of this and you get force, right? Because if you stretch it to the right, the force is to the left, but you're storing positive energy in that case. So this is just in addition to what we've already decided with these things, okay? One of the applications that we'll look at with this potential energy well idea is, let's say I'm on the Earth's surface and I'm here and I want to escape, meaning I want to launch a rocket and I want to get out of our gravitational field. Well, we're going to look at conservation of energy, right? We're going to get rid of drag here. That would make it way too complicated. The energy I have at the beginning is some sort of potential and some sort of kinetic. And I want to launch it, and then it'll have those two things. Oops, that's a final. And then some KE final. I want to find the minimum speed. The goal here is to find the escape velocity. The escape velocity is the minimum speed I have to launch something with, or like I'm going to chuck a basketball. How hard do I have to throw it in order to escape the gravitational field? Well, my original potential energy is G mm over r. The kinetic energy I need to launch with is 1/2 mv squared. And then if I escape, I get no potential energy. And if I'm launching it at the minimum speed, I'm going to have no more kinetic energy on the end as well. So if I solve for this v will end up being the square root of 2gm over r. And it shows the nice relationship between the mass of the planet. The more massive the planet, the bigger the gravity, thus the faster the escape speed would have to be. And the bigger the radius, the smaller the velocity, because you're already further away from the center of mass. So this is our escape velocity. You don't have to memorize it. You should be able to derive it. But you can check out the units. The units are going to make sense. And then we'll also start talking about orbital stuff. But in this video, I just wanted to show, looking at our force equation, and this is our new potential energy function. Again, you have to use this idea when you're talking about satellites or moons or anything orbiting or rockets. You can still use this, mgh, but mgh goes to when the force is a constant force. If the force isn't constant, which it's not if you start increasing your r too much, then you have to get a new potential energy function. We'll look at situations where we have different graphs than just this particular graph, but hopefully you can see the connection between that. The potential energy is the negative accumulation of force, and that force is the negative derivative of that change. Again, go back to old school. If you increase your potential energy, you increased it because the force was in the opposite direction. If you take a spring and you stretch it to the right, meaning that the spring force was to the left, you were working against the spring while stretching it, you then stored a positive energy. And so that relationship is true.